Hello, Amsterdam. How are you? It's so great to be here and to enlighten you about my passion, which are the stars. And so let me start by saying that the stars are really important for you. You should be grateful to the stars. You have been drinking cocktails, I think, or are still doing it, and will be doing so later. Well, everything in these cocktails is made by stars. So you really should be grateful, right? You may be completely differently motivated than me. Why you care about stars? They are simply beautiful. They are inspirational. They are vital for your cocktails, right? Why is that? Well, let me put up a chemical table. I'm sure most of you have learned about the chemical elements in school, but here's just a reminder, This fabulous table of Mendeleev has all the materials that we know here in our life since the Big Bang. So every box is a chemical, right? In the Big Bang time, there was only hydrogen and helium. Very boring. The hydrogen was important for your cocktails, though, right? But all the rest, which was even more important for your cocktails, is made by stars, right? Until the present day. And you see different colors here, mimicking different kind of stars. And so, how can stars do this, This is an important question. And so let's look at that, since you're in an experiment tonight of drinking some of these materials. Let's start with the star we know best. That's our sun. The sun is our home, host star, as we call it, right? The sun was born about 4.5 billion years ago. And here you see its life path, that it's going to follow. It's about halfway, as you see, indicated here, and it shines light, as we saw in the intro movie. It creates light, it creates energy, and it can do that thanks to the fact that it's a big, hot, gaseous sphere that is very dense in its interior and very hot, right? So in the interior of the sun, what is she doing right now? Well, she's creating nuclear energy. How does that happen? You have material, hydrogen, the easiest element that was at the upper left of the chemical table you just saw. And it pushes these hydrogen atoms together with such a high density and high temperature, typically 15 million degrees Celsius, or Kelvin, doesn't matter what you use at these temperatures. And it pushes that together to create a helium atom, the second simplest chemical element that was on the upper right of the chemical table. Now, in helium, you see 4 of these nuclei, as we call them, and 2 electrons. Doesn't matter if you don't recall what these particles actually are. But the bottom line is, if you add the mass of these 4 constituents together and you compare it to the mass of a helium atom, then you lose a tiny, tiny, tiny little bit of mass. And if you take that tiny little bit of mass and plug it in Einstein's most famous formula, it's about the only formula I brought, so no worries. Tiny little mass times the square of the speed of light, then you get energy. And that's the energy that you see from all the stars with your eyes. Your eyes are beautiful detectors, right? Now the sun is thus in its middle part where it's hot enough, not on the outside, because there it's only a couple of thousand degrees, but in the inner part where it's 15 million degrees is a fantastic nuclear reactor. Stars are champions in creating nuclear energy. We are lousy people who can't do that properly, okay? Now, how long will that last, this creation of helium? Well, it will last as long as there is hydrogen available in that inner core, right? because if there's no more hydrogen, then you can't do this nuclear reaction. Right? And so how long can the sun still do that? About halfway through her life. So still several billions of years. Huh? And so this is quite a boring life of our star, which is why we are here. Huh? It's a very stable environment. Huh? Now, when the sun will hit her first energy crisis, so that means that the inner part of the sun will have become completely helium and there's no more hydrogen, right? Then she's gonna have to care about the energy crisis. Why? Well, if there's no more nuclear reactions and light particles, photons, moving outside, then gravity is gonna win because it's gonna pull the sun together. And so the sun has to come up with a solution against that. What can she do? Well, there was this whole table of chemical elements. So the solution of the sun is, oh, I'm going to try to fuse helium and turn it into a heavier element. But for that, it needs to be 10 times hotter. Right? So you can fuse helium, helium particles, and turn that into carbon, a critical element for your cocktails, but also for life, right? And then further on, nitrogen and oxygen. I have a dress with oxygen because I need oxygen to perform, right? When can the sun do that? Or under what condition? Well, she has to shrink her helium ball that sits in the interior to make it 10 times hotter. Because if you push material together, then you make it hotter, right? We're not going to experiment that in this theater, but I could basically put you all closer together. You would also heat up, right? Now, so you can create carbon, nitrogen, and oxygen. The sun is going to do that at the phase when she's a red giant. This is not going to be pleasant for you. But you don't have to worry about it because in several billion years, I'm sure we will have, fucked up this planet already by that time. Right? So I'm afraid we're not going to make that time evolution a reality, and for sure in our lives we will not. Right? It's going to happen though. And then towards the graveyard, the sun will die out once there is no longer any helium, because then it will all be carbon and oxygen in the inner part. And in order to fuse that, you have to make it even hotter, but the sun doesn't have enough mass to reach that goal. So she will actually end in the graveyard as a white dwarf, as we call it. What is that? That's an object that is about as large as our planet, but carbon and oxygen put together under very high pressure. And I don't know if you know what you get in that situation, but the reality is diamonds. So the sun is going to end her life as a diamond in the sky. Right? We will no longer be around. Now, what is the problem, or what is the challenge? When I showed you that chemical table with all these growing curves that show what kind of material stars have made, I was actually hiding a little bit of the storyline, because these predictions in each of these boxes, they fully rely on our models of stars, right? And our models of stars for sun-like stars are not too bad. So stars get born, they live like the sun, they become a red giant. You understand now why. They swallow their planets, including the humans that might be there, and then they expel their outer layers and go to the graveyard, right? This happens in like 10 to 11 billion years for a star like the sun. But a star that is born with much more mass, way more gas, like typically 8 times more than the sun or up, lives a much faster life. Fast in astronomy means only a couple of million years, right? And these are going to explode and make much more material. So if you paid careful attention in this chemical table, the hot massive stars are the real metal producers of this universe. Again, entering in your cocktails. And their graveyard is after a supernova explosion. A neutron star or a black hole is the graveyard of these stars. Now, so these stars are much more fun. They are much more energetic, and I like them more. So I study them, right? If we are honest, everything, almost everything in astrophysics relies on stellar models, as I've written down here. Now, these models are far, far, far from perfect. And so I want to show you why we're going to do better than what we ever did before until about 10 years ago, a bit more. What is the problem that we face? Here I'm showing you results of our computer models that mimic how stars live. And for your knowledge, stars can have a mass of about 1/10 of the solar mass up to more than 100 times the solar mass. And so depending on their mass, the stars also have a different color. You can't see that by your eyes because all stars are tiny little dots and they just look the same. But in reality, they look very different when you analyze their colors. Now, the sun here, you already know, it will get about 10 billion years, 10 to 11, let's say. The less mass a star has at birth, the longer it lives. Right? So these very tiny stars, they still haven't had time to evolve in this universe, in our universe that we live in. Well, these big stars, well, many, many generations have passed since the Big Bang. Thousands of generations, and they have produced all these wonderful elements that entered into your cocktail, right? So these are the ones you should be grateful, okay? Now, in order to deduce that, everything that I'm telling you assumes that these stellar models that we have are good, or the truth, or reliable. And I have to disappoint you in that. They are not. And that's the problem, right? How do we know how good or bad our computer models of stars are that are used in the whole of astrophysics, basically, right? We can only see tiny little dots in the sky, and the light that they emit comes from the stellar surface, right? Just like we see the solar surface. But the real interesting physics and chemistry happens in the deep interior, in that nuclear reactor, where it's millions of degrees. But how do we know this? And how can we test our theories and our models? Right. Now, this is a bit different for different stars. And so, again, you have these tiny little stars that are very turbulent. The energy that's produced in the interior is really, I call it boiling gas. It's a bit like the kettle, water kettle on your stove in the kitchen, right? If you keep adding energy at the bottom, it starts to boil, right? And everything mixes very effectively. These tiny little stars do that. These major big stars, they have a different way of getting their energy out. We call it diffusion of photons, right? And somewhere in the middle there is this layer where you transition from a quiet diffusion of the energy to the violent boiling core that they have, right? And so the sun is somewhere in the middle, right? And for the sun, for someone in the audience, this is called the tachocline. This is a layer where you transform from this boiling kettle to something that diffuses out or inwards for the sun. Right? Now, the position of these layers is critical to predict the life of the stars. But we can't directly go and measure it, where these layers are. Why is this critical? Because if it is like boiling gas, then everything is fully mixed. That's a bit like your cocktail, right? I don't know what you ordered, but if you want all those materials, particularly the alcohol, to be fully mixed with your soda or juice, what do? You stir, right? Why? Because if you rotate, then everything gets mixed much more effectively than if you wouldn't do that, right? In my language, that means that you bring angular momentum to your cocktail, right? Remember this. Now, stars like the sun or lower mass happen to be slow rotators. We see that from the outside of the sun. Huh? If you ever look at the sun, please with protection glasses, evidently, there are solar spots, and if you're patient, then you can see them reoccurring in your line of sight. And from that, we can deduce that stars like the sun, for instance, they rotate with a period of 26 days. I call that slow. Right? These stars, they rotate very fast. When I say fast, I mean really fast, 10 times faster, right? And so, if you have fast rotation, then you mix more effectively. You experience that from your drinks. And if you mix more effectively, what's the consequence? Then you can bring fresh hydrogen into the core where the nuclear reactions are going on. So you can live longer. And so this is connected to the ages of stars. Now, the age of a star is very hard to measure. You only see that tiny little dot, right? So this is something that we need to understand better. Yeah? This was already realized by Eddington, and Eddington is sort of like the godfather of stellar structure and evolution. And in his book, next year we celebrate 100 years, as you see, last century. He was a bit frustrated because he knew that stellar models would not be good, or at least not be well tested, if we only stick to the stellar surface and the photons that reaches from the surface. So he asked, what appliance can pierce through the outer layers of a star and test the conditions within? Well, I'm a little bit proud to know the answer now. And I've even had a share in finding the answer. Right? Asteroseismology is the answer. What is asteroseismology? It's the study of starquakes, if you like. You saw the intro movie. Now, why is that so important? Well, it's just like earthquakes in a certain way. An earthquake creates waves. It travels through our planet towards its interior. These waves bounce back at the iron core in our planet. And by measuring that, this is actually a measurement done in the Netherlands of an earthquake, or the waves created by it. Earth seismologists can learn about the physics and the chemistry deep inside our planet. You know, it would be sort of like easy if we could just drill a hole here until we reach the core of our planet. Then we could test it, right? We can't do that technologically. That's just a no-go. Well, I can't go and fly to a star and dive into the gas and do the experiment, but I can learn more about the waves of stars than we can do for our own planet, or our own sun for that matter. I still find that amazing by the day. And so here is a star that is undergoing what we call stellar oscillations. What you see here, the brightness of the star, indicated in blue, and how it fluctuates, right? So this is a seismic measurement of stellar oscillations, also called starquakes for analogy reasons with the Earth. You see why. And so you can see that this is a measurement. It's done by the NASA satellite called Kepler during 15 days. But in reality, we do not have 15 days, we have 1,500 days. So 4 years long, uninterruptedly. And there's not just one star, no, there are 200,000 stars for which this satellite delivered us data. And so that has opened a completely new field, which we call astroseismology. So what do we actually do? Well, you have these up and down motions. It creates waves, and these waves propagate inside the star, inside the cavity. Just like I'm producing sound waves now, and you can hear me. Why? Because we're in a cavity, a theater, that has air. And so I am talking all the time, and I get some help from a microphone. But the sound waves can propagate here. Now, of course, there is no air between us and the stars. Yeah, it's a vacuum. So we can't hear that with our ears. That's a shame. That would be even better if we could do that, but we can't. But anyway, deep in the interior, we have these waves like this green one, this red one, this purple one, you see, and they bounce back and forth. Yeah. And the way they bounce back depends completely on the pressure and the temperature of the gas inside the star. Just like my sound depends completely on the temperature and the pressure of the air inside this room. Okay? So, what we want to do is sort of measure these waves, and as said, we can't hear them. But we can make animations of them. And here is to make you a little bit dizzy if you stare at these. Stars are hot gaseous spheres, and so if you perturb a sphere, and I'm exaggerating with my hands, you get these blue and red motions, and stars also rotate, as you see. So, you know, the blue parts are coming towards you at a certain instance. That's why they are blue shifted. The light is blue shifted, just like the sound of an ambulance gets higher frequency when it comes at you. And it gets red shifted for the parts that are moving like towards the interior of the star is away from you, right? And so this happens with certain functions which we mathematicians, we love functions, spherical harmonics they are called. Why? You have a sphere that without starquakes would be completely spherical, and the starquakes make it deviate from its spherical symmetry. So then you automatically end up with spherical harmonics. And you see these white bands that contains gas particles that do not move, and the red and blue are moving towards you. Very tinily. I'm exaggerating a lot with my hands, right? And so we call these non-radial oscillations. But of course we can't see that directly because the stars are tiny little dots. For the sun, we can resolve the surface. So helioseismology is for that reason most advanced, right? Now, how do we deal with asteroseismology? We want to measure waves. Hi, oh, I also get a cocktail. That's great, and I'm going to stir it, but later on, because else I'm going to spill. All right, that also means I have to hurry up a bit. Oh, how do we do that? I tend to get over-enthusiastic. We have space missions delivered by NASA and ESA that operate above the Earth atmosphere, and we measure these tiny little starquakes. 1 in a million is the variation. So your eyes can't see that for the sun because they're not sensitive enough for that. But as you see, we have space missions since 26. That's great. Who can deliver us these light curves? And then we do a little trick. So here you see that same star. It's a bit more massive than the sun. And we mathematicians, when we have time variable phenomena, we love Fourier transforms. So that's a mathematical trick where we change this light curve into its frequency spectrum, as we call it. And then what you see here, you see the amplitude, the strength of the starquakes as a function of frequency for this particular star. Okay? So that's basically one transformation that we do from the data. And as you all know, 1 day is 24 hours. It's that many seconds, right? And if you do the inverse of 86,400 seconds, then you end up with a frequency of about 12 microhertz, right? Can you hear that? No, you can't hear that. But I'm still gonna do a musical intermezzo, and I'm gonna put you right in the middle of the sun so that you can hear the sound waves of the sun, right? It's not pleasant there, but let's pretend we go there, and I have to do a little bit of a trick because your ears can't hear that sound. They are not in our audible regime. So what I've done is make all the solar quakes shift by a factor 100,000, right? That's just to make it audible. All right, so let's now experience this, something we can't do because there is vacuum between us and the sun. But if you were in the middle of the sun, you would hear this. Are you ready? There was a musical band before. I think you may have liked that more. Yeah, at least I do, right? But this is such a pleasure for us seismologists. Oscillations ranked as a function of frequency, and every black stripe here is a tone of a sound wave that is created by the solar quakes. And what do you see? Well, the strongest one is about here, 3,000 microhertz. If you turn that upside down, then you have a periodicity of about 5 minutes. So every 5 minutes, that most important solar quake makes the surface of the sun move up and down with a strength of 1 in a million, right? Now, what will the sun become when she has no longer hydrogen in the core? A big red giant, right? If you make your instrument bigger, will the frequency go up or down? This is a real star, huh? I'm not fooling on you, it's just the same 100,000 factor, right? This is a red giant bass. It has lower frequencies, and you had the right answer, so you're all already seismologists. The dominant frequency occurs around 68 microhertz, way lower than for the sun. And then in the graveyard, all that's left is a tiny little ball, carbon and oxygen, in the size of the Earth. How will that sound? This is the piccolo, okay? So by listening to this is a piccolo in a room, in a cavity that is dominated by helium, carbon, and oxygen. The chemistry also plays a role, okay? About 7,000 microhertz, higher frequency. So you have learned now that if you were to be able to listen to the music of the stars, you would know how big the star is, right? And so again, for the sun, this dominant frequency tells you immediately how big the star is. Well, it's a tiny dot in the sky, right? Now you also see that there is some regularity in this. This is the symphony of the sun for me, right? All the frequencies of the waves. Depending on the dominant forces in the star, and I've listed several here, 5 of them, the frequencies have different values. And so for the sun, this is the simplest case. It's acoustic waves that you're very familiar with. Musicians know this very well, okay? We will turn to other stars later on if I get the time. But you understand now, hopefully, how we can size the stars. But we know how big the sun is. We can measure it because we see it in the sky and we know how far it is. And so it turns out that by measuring another star like this one, whose signal you see here, we can rank the stars, just like we can rank musical instruments. And here you see that for 4 stars. We know that we have a calibrator, the sun, and then we come to the conclusion that we can measure astroseismically the stellar radii up to 1% precision. This is unique, okay? Now, we can do more than that. Here is a star that is supposed to be a copy of the sun. When you look at its exterior layers, it's a copy of the sun. And you see its frequencies and the beautiful colored red here, frequencies of the sound waves that it plays in its interior. Where is the strongest one? Well, about here, 2,150 microhertz. The sun was at 3,000. So is this a bigger star or a smaller one? It's bigger. It's not a copy of the sun. Those who study the outside layers of stars had it wrong. We seismologists know it's bigger. And if it's bigger, it means it's older, because it's already on its way to become a red giant. Okay? So we can derive the radius, the age, and if you have the radius and sound waves, they depend on the density. So if you have the radius and you measure a pattern for the density, then you know the mass, right? Mass divided by volume is the density, if you recall from your physics classes. So we also know the mass with 2% precision. This is impossible to do without solar oscillations. And so now we do this for all the older stars and the bigger ones in the galaxy. These are red giants, all measured in frequency. Yeah? And so this star, 250 microhertz. That's a bigger star than the sun, huh? 10 times bigger. And this one is even a bit bigger and a bit bigger and a bit bigger, right? Because it keeps going to lower and lower frequency. So this is a series of stars that differ in ages by several million years. So it's stellar evolution in action. We can't wait in the career of an astrophysicist to get there, right? And so these stars are very big, so we can see them everywhere in the galaxy. And that allows us to do galactic archaeology, as we call it. Huh? Age dating stars and seeing them throughout the galaxy. So that's great. Now I come back to my cocktail, and yours, and to the rotation and the rotational mixing, right? So these stars rotate. And you know very well what happens with sound waves. I will not do the experiment, but I could start running around now. And for you, that would be awful, but for me as well, right? Why? Because the sound I'm producing would be at different frequencies. And musicians know this very well. Huh? Huh? They don't want to be on rotating podia as a symphonic orchestra, right? So rotation changes the frequencies of the waves. And it does so very tinily. Look at here, 0.2 microhertz shifts. You need a long time before you can measure that shift because it's so tiny. And so that's what we realized we could do. And so here's the sun, here is what it will become. And by measuring these tiny frequency shifts, you can sort of open up the star and understand how fast it rotates in its interior. Yeah? And so this is amazing. These stars are at, very, very far distance. We measure their frequency. We measure the shifts due to rotation, because then you get these splitted frequencies, as we call them. And we can measure how fast the interior is rotating. This is an animation by Paul Beck, who was my PhD student. It got him a Nature paper, and I'm still very proud of him. This is 2012. That was the first time this was achieved. Now, let's move to some more difficult cases. These fast blue rotating stars, right? And so we know from the exterior layers that they rotate fast. What we found is that their waves are dominantly restored by the gravity force. They are big, massive objects. So they actually have slow waves in fast rotators. That's way more difficult mathematically, right? So here is the frequency axis. The sun was at high frequency, 5 minutes up and down, and 26 days to rotate around. If you divide 5 minutes by 26 days, that's a tiny little number, right? It's tiny. You can pretend that the sun is not rotating if you treat the equations mathematically. But on this side, you have stars that have their quakes by a periodicity of a day, and they rotate in a day or two. So we cannot ignore the Coriolis force. Yeah? That's the same force that makes your bathtub spiral inwards differently in the northern hemisphere than in the southern hemisphere, right? So my stars, so to speak, are in this frequency regime. And that's something we were not aware, because we cannot rely on the sun to interpret these oscillations, right? And so here's a beautiful, beautiful gallery. Again, 7 stars, I think. Gray are the data from the NASA Kepler satellite. Frequency, you know, meanwhile, what that means. The red is the Fourier transform, so that's the symphony. And you see, again, a pattern. Yeah? The pattern before, where I had these red giants, was from big to bigger to bigger to bigger, right? Old to older to older to older. This is a completely different signature. Here we have a slow rotator. And in going down, we see the frequencies get shifted. Why is that? Well, you have these up and down motions, and this is a wave that passes along with you. Now, if you rotate fast and this wave comes along with the rotation, then it occurs in your line of sight faster, right? So that happens at a higher speed, so to speak, right? So it shifts to higher frequency. And that's what you see here. This lower star is a fast rotation. And so by measuring these Fourier transforms, well, we measure the light curves and turning them into Fourier transforms, you can immediately deduce the rotation of the star. And that's not the surface rotation. No, it's the deep interior rotation. Right? We could do this for a giant since 2012. We can do that for these fast rotators since 2016. Again, thanks to the hard work of several of my PhD students. Now, where's the assembly? Here is where we are. This is a diagram of the internal rotation of stars as a function of the evolution of the star. And each and every dot in this diagram is a real star where we have applied this. And we, that means a whole community of very young scientists, which I keep on repeating. Some oldies like me also did some contributions, but every single dot, and there are 1,800, is damn hard work of many years, okay? Before 2012, this diagram was empty. There was nothing. We had no clue how stars rotate. So I'm very proud that we see here so many stars, young stars, and then when they don't have any nuclear fuel anymore, they evolve to red giants. And what you see, it's like an ice skater. The star gets bigger and slows down. Ice skaters do that to make a pirouette, and then they, right? That's when they go to their graveyard. Neutron stars are really super fast rotators. We can now measure that from the waves, all right? So where does it stand? Well, what do we do in our daily life? We have observations from beautiful space missions. We measure the seismic signal. We Fourier transform. We see the frequencies of the waves, and these are the observations, right? On the other hand, we have theory. We are good computer builders. We write code. We love that. It's computational astrophysics. We create stellar models that are in equilibrium. We make them vibrate, and we produce theoretical predictions of the frequencies. And we compare them. That's what we do, right? And so our theory was wrong up to a factor 100 in the rotation frequency. We couldn't measure, so people sometimes they are completely disappointed. No, I'm happy when it doesn't work, right? Because we can learn something. And so proud to say we have now by far better stellar model in terms of rotation. And we keep on increasing the sample, right? Are we done? No, we are not done, right? Because there is yet another force, a force that has to do with a magnetic field. We call that the Lorentz force. And this creates asymmetry, because the rotation sort of splits the frequencies in your line of sight. You have understood why. But now I add another force if there is a magnetic field in the deep interior of stars, and these fields are buried, right? And then we get an asymmetric splitting. We have just discovered, and I'm talking 22, see? 23, 24, this is yesterday for an astronomer, right? That stars harbor strong magnetic fields in their interior, but not all stars. We can measure it in 2% of the stars. And we don't understand why that is. So we have lots of work to do, but we do see or measure that we can have the strength of this magnetic field from the seismic data, okay? What do we have to do? We also have to acknowledge that these massive stars, what you see here, is a diagram, scientific diagram. The percentage of stars that are in binaries as you increase the mass. And here you see 0.01 smallest, lowest mass stars to higher mass stars. And when you're here in this side, what do you see? 80% of the stars are in binaries. That means they have a companion. And what do you get when you have a companion? You know that very well, huh? We also have a companion as the Earth. Our moon is our companion, and it's thanks to the moon that we are here, by the way. So not only be grateful to the stars, but also to the moon. The moon stabilizes us. That's another lecture. 80% of these massive stars are in binaries. I cannot afford to ignore the tidal forces. Just like we know what tides do with the fluids on this planet. Admittedly, we have yet to develop tidal asteroseismology. So do stars do this? Yes, they do. Here you see 3 measured cases. The orbital motion is in this red curve. And on top of that, you superpose oscillations, right? And so that's tidal asteroseismology in action. The data tell us, and now we have to develop good theory to interpret it. And that's easier said than done because we have to add another force in these complex equations to solve. But the stars do it. And so that's both a challenge, but also allows us to improve the models for closed binaries. And then something I'm extremely proud of, because as it turns out, stars rotate way faster than the sun, huh? As I said, 1 to 2 days. And what do you get when you have a gaseous ball of fire, literally, that rotates fast? It gets flattened. It turns into an egg or a baseball, if you like that better, right? Now, all of what I've shown so far is asteroseismology, assuming that in equilibrium the star is a sphere. Spherically symmetric. And that's not good. It's simply not good. We have to work with 3 spatial dimensions. This sounds easy, but it's not. And I'm a product of the European Commission because I just received a big bag of money to develop seismology of flattened star. And I want to thank you as taxpayers because it's your money. And that allows me to do my hobby. Yeah? Even more of your money for the future of the seismic data that's coming at us. We're building an instrument. It's right next door in Noordwijk in the clean room. You see me standing here. It's a big machine that we are building to do a whole lot of more and more precise astroseismology. And fingers crossed, it should get launched very soon. So in the end, to conclude, here's my end diagram. I'm very proud of this fountain of opportunities. I'm very proud of our community. It is super young. I'm among the oldest. That's nice when you see all these young people. Whatever is being your topic in astrophysics nowadays, whether it's like tides or the galaxy, exoplanets and the search for extraterrestrial life, super interesting. We do that by the day because these host stars do have starquakes. Even gravitational waves, because that's the graveyard of these binaries. Huh? All of these topics benefit from astroseismology, and that is something that was unimaginable 10 years ago. And I thank you for your attention.